So again, exercise 3, problem 3, and in this problem, this is the first problem considering a transmitter-receiver system, and there we will make ourselves familiar with some very important parameters of a transistor receiver system, and also we will discuss the change between the linear scale and the dB scale. And here it's written a transmitter transmits a power of 20 kilowatt. So we have here a power which normally I call P1. This will be the power which is transmitted by a transmitter, and it's said to have a 20 kilowatt of power. It would transmit a power of 20 kilowatt, and with an antenna showing a gain of 5 dB. So we say now G1. G1 I use normally for the gain of the transmitting antenna, and you see that the gain of the transmitting antenna is given in 5 dB. So you have here, it's given in the dB scale. So now we always must distinguish between the linear scale and the dB scale, and here is calculate the value of its EIRP in the direction of the main beam. So EIRP or IERP is the isotropic radiated power. And of course this isotropic radiated power is only valid in the direction of the main beam. So you see you must calculate now P1 times G1. But this equation is only valid in the linear scale, not in the dB scale. If you would insert now, for example, 5 dB, then you would get as the unit kilowatt times dB. In this makes no sense, this unit. So what we have to do, we have to change G1 into the linear scale, and we know that we have the relation that G1 given in dB is 10 times log G1. So this is the notation I use to convert the linear scale into the dB scale, and I want to point out this equation from a mathematical point of view. It makes in principle no sense, because you see we have in each time the same the same parameter here, but from a physical point of view it makes sense, because I just say I can have a look on the gain in the linear scale or in the dB scale, and here this equation now gives you the how you can convert the linear scale into the dB scale. So of course now we have it given in 5 dB, so we must resolve for the linear scale here, and you see I first have G1 divided by dB, and this I have to divide by 10, and that would be equal to logarithms of G1, or I can say G1 will be 10 to the power of G1 divided by dB divided by 10. So I will do this here very much in detail. So you see, if I say G1 is now equal to, you see, if I insert G1 in dB, of course then the dB will cancel, and then we have just here 10 to the power of 5 divided by 10 or it's 0.5. And you see here, this works only if I have G1 in the dB scale, then it will cancel and you can take the power of just the number. Otherwise it wouldn't work. And so this is in principle now the equation how you can come from the dB scale into the linear scale. And in our case, of course, this would be equal to the square root of 10, and this is round about 3. So this is 3.16. So G1 now shows a value of 3.16, and this value we can insert into this equation, and then we can get for the EIRP that we have 20 kilowatt times 3.16, and if you calculate the value, then you will get 20 times 3.16, it's 63.2 kilowatt. So this will be the isotropic radiated power in the direction of the main beam. So again, you see the purpose of a transmitting antenna is to focus the radiated power in a certain direction, and this is called is normally the main beam. So, and if I have a power of 20 kilowatt, and if I have a gain of the antenna of 5 dB, then it seems that into the direction of the main beam, the transmitter radiates a power of 63.2 kilowatt. So, are there some questions now concerning this task? So, there seem to be no questions. Then I write here the isotropic radiated power. In our case, it's 63.2 kilowatt. Of course, this power is only radiated into the direction of the main beam. So the next question is now calculate the power density and the amplitude of the electric field at the distance of 10 kilometer in the direction of the main beam. So as soon as we know the isotropic radiated power, then we can assume our isotropic point radiator, and we know that the time averaged power density will be now equal to the isotropic radiated power divided by the area of the sphere at this certain distance. So this is then 4 pi r squared. So this is 4 pi r squared. And of course we can now insert the numbers here. This is 63.2 0.2 10 to the power of 3 watt divided by 4 pi, and the distance is assumed to be, what did I say, 10 kilometers. So we have, this is 10 times 10 to the power of 3 square, and we have here meter square. So of course you have to calculate these numbers, and yeah, I can do it. 63.2 10 to the power of 3 divided by 4 divided by pi divided by 10 to the power of 3 square, and then we will get, this is S, the time average pointing vector will be, you see, we are not interested now in the direction, but only in its absolute value. It's 5.03 10 to the power of minus 5 watt per meter square. This will be the power density due to our transmitter, which radiates an isotropic power in the direction of the main beam. So in the direction of the main beam at a distance of 10 kilometer, we will have this value for the power density. Are there some questions here?
So this is the time average pointing vector, right?
Yeah, this is always, if we deal with the pointing vector, we are only interested normally not in the instantaneous pointing vector, but in the time average pointing vector. So it's the same if you are doing a cooking with the with an electric oven, though, then you are only interested in the time average power which goes into your cooking facility or something like this. So yeah.
But in your script, you don't use the bracket for the average, right? It's just the same thing, right?
This is, I have a look here. What did I do in the script? Yeah, I'm sorry for this. This is correct. So, now this is identical to S in the script. No. So this is, I should perhaps use, if I use the script, or if you have a reference to the script, then I should use just S. But why did I do it like this? So I'm just also giving a lecture on field theory, and there I want to distinguish between the time average pointing vector and the instantaneous pointing vector. So, but in RF engineering, we normally only use the time average pointing vector. Are there further questions? Yeah.
Here, because the radiated power is equal to the the integral of the power density with the area, right? But here we only divide it by the area of the whole sphere. So are we assuming anything to be uniform?
No, you mean this equation in principle now?
Yes.
Yeah. So this is the you must in principle remember the definition of the isotropic power radiator. Oder sorry, not isotropic power radiator, but isotropic point radiator. So I first define in the lecture the isotropic point radiator. Perhaps I go back to this. So I delete. Oh, now perhaps I have to first. I have to write our result here, so I don't forget the result. So we have here. Now then, I use just S here. S is 5.03 to the power. Oh, sorry. I write it here. S of perhaps 10 kilometer. I write it's, what was it? 503 10 to the power of minus 5 watt over meter squared. So perhaps I just explain a little bit again the isotropic point radiator. So, of course, the problem concerning or dealing with antennas is that if I really wanted to explain the behavior of the antenna, I must go into the from the physical point of view, I must go into the Maxwell's equation and solve all these equations. And of course, this is very complicated. To really calculate the how an antenna is radiating the power. So, from a system point of view, it's not so interesting how it radiates. Just the fact that it radiates is of interest. So, the idea is that I have a point in space, and out of this point we get the radiated power P1. This is like a fountain in space, but only in a point, or you can imagine a light source as a point. If you would have a light source in space, this is just a gluing point. And then you assume that the power of this point is isotropically radiated on the sphere. So we can, here I can now quite easy calculate S. So I'm only interested in the absolute value of, not in the direction. So in our direction it would be ER. So in the script I inserted here ER. But from this idea you can say that S is just P1 divided by 4 pi R squared. This is the behavior of an isotropic point radiator from a system point of view. Now if we have a real antenna, then we can say the real antennas are always used to focus the power in a certain direction. And this behavior is described by the gain of the antenna. So, for example, this is the main loop, or this is called the main loop. Or main beam, And of course here we have some side loops normally. And I assign, so if I compare this now to the isotropic power radiator, then it seems that more power is radiated into the direction of the main beam, main loop or main beam. And here, this is described by G1. So in the direction of the main beam, the antenna focuses the power which is radiated in the direction of the main beam. And to describe this power or this purpose of the antenna, we say in the direction of the main beam. Of the main beam here, we will have the power density S of R, which is then G1 times. So here comes now the gain of the antenna, P1 over 4 pi R squared. So, and here you see now this seems to be, or this is then called isotropic radiated power, because now it seems that much more power is radiated if I assume this to be a point radiator. Now, did this explain the questions? Or did this help you to understand the isotropic point radiator and the gain of a transmitting antenna, for example? Or are there further questions?
So it's like so the S of the real antenna is like the gain times with the S of the isotropic, correct?
Yeah, though in the direction, though this is very important to understand, in the direction of the main beam, it seems that with the help of this antenna is more power, more isotropic power radiated. Here you have in principle now the effective isotropic radiated power. So it seems that in the direction of a main beam now a much higher power is radiated. But in total, of course, this is now again, if I insert this here in this equation, then I assume again an isotropic point radiator. Good. So, further questions? So then, I delete this again here. And of course, the next question is quite easy again. So here the question is in the task is calculate the amplitude of the electric field at a distance of 10 kilometers. So if you are very far away from the antenna, you always can assume that the field or the radiated power now forms a plane wave. So if we are very far from the antenna, now this is called the far field of the antenna. In the far field of the antenna, the field of the antenna behaves always as a plane wave. So we can say that the time average Poynting vector again, we can say that to calculate the time average Poynting vector S, we can use the equation. This is 1/2 absolute value of the electric field square divided by Z naught, or we can say this is also 1/2 always the absolute value. This means we have here the amplitude of the electric field divided by Z naught, and so we can now calculate the amplitude of the electric field to be, this is 2 times Z naught times S, and we have to take the square root out of it, and this gives us the amplitude of the electric field. So we will insert the numbers again. This is 2 times 377, and we have here volt over ampere, and here we have now S, it's 5.03 10 to the power of -3, and it's volt ampere over meter square. And of course you see here the ampere will cancel, and we will get as a result volt over meter after taking the square root, and the value will be now 0.195 volt over meter. So this will be the electric field of our of the power radiated in a distance of 10 kilometers. We will have this field strength. So are there some questions here? No. So, sorry, here I did a slight mistake. It must be written 10 to the power of -5, but nevertheless the result is identical.